Okay, let's get started. Our next speaker is Nathaniel Trask from Center for Computer Research at Sandia National Labs. He will be talking about generalized mean least square nets, which is a machine physics-informed deep learning method using unstructured data. Thank
you. Okay. Thanks, Harry, for the introduction and the invitation. So I'll get started here. So first off, I'll introduce what scientific machine learning is. And it's basically a discipline that lies halfway in between traditional scientific computing and traditional machine learning. And the interesting challenge to it is that you are somewhere in between having small data and lots of physics and big data and no physics. So unlike traditional scientific computing, where you might have a known model, known discretizations, mature tools and mathematics or how those work, and also where data is primarily just used for validation and verification. On the other end of the spectrum is traditional machine learning, where you don't know anything. You just have some black box that generates data. We're lying somewhere in between, where you have some known model form. For example, you might know it's a conservation law, but you have an unknown constitutive relationship. And you might only have a small amount of high fidelity data in order to figure out what that constitutive relationship or closure is. So typically this is characterized by sparse data, and that's because training data might be expensive. It might come from very large scale DNS synthetic sources, those sorts of things. Might be experimentally intractable. You might only be able to get partial probes of a system experimentally. And then another challenge about scientific machine learning is that data is typically highly unstructured. So unlike traditional machine learning and computer vision tasks, where you have images where data consists of Cartesian grids of pixels, of point values, of color intensity, and so on. In scientific applications, your data might come from an unstructured finite element mesh, for example. The samples might be represented as differential forms. For example, it might be the flux through faces of a mesh from a finite volumes simulation. And it also might come from Lagrangian probes, drifters that are flowing through a field and so on. So the fundamental problem for scientific machine learning is what we're calling operator regression. And so the way that works is you have a collection of functions, U, belonging to some Banach space V, and you have some functional tau belonging to the dual to that space. And the idea is we want to infer what tau is from observations of how that operator acts on functions within that function space. So for example, you have a basket of functions, and then you get to see that the action of tau on those functions looks like this. And so you want to be able to say something like, that operator was a gradient. So the way that we do this is we set up a regression problem where we come up with some candidate family of models, which we denote with a script L subscript C, and that C denotes some set of parameters. So for a neural network, that might be weights and biases and so on. And so the whole objective to this framework is, can we come up with a good family of models and then use them to learn operators from observation of their action. So what applications can be characterized like this, with this operator regression framework? You can look at data-driven model discovery, numerical homogenization, and surrogate model development. All these applications, it's very difficult to do rigorously, and the hope is that some data-driven techniques might be able to provide the same kind of capability without all of the mathematical complexity and some of the shortcomings. So for example, you might take particle data, something that comes from something like molecular dynamics. In this case, we're looking at Brownian motion. You might do a short burst of simulations, which are extremely expensive, in up the particle density into histograms, and then try and learn a PDE, which will evolve the, for example, the mean density in a much cheaper manner. And so what we'll do for this is we'll assume a form for the dynamics. So we'll assume something like the time derivative of the field is equal to some unknown operator. And then we'll use the high fidelity simulation as an example for a discretization of this ODE. So the tool that we're going to try and generalize to come up with a framework for this is convolutional networks. And the idea behind convolutional networks is you're trying to parameterize an operator in terms of some kernel. So the idea is we're going to perform quadrature on this convolution operator over a Cartesian grid of points. And we're going to parameterize that kernel by assuming that it has a form that looks like this. So that when you evaluate it at a node I and a node J, it takes this form. And so the discrete form for the operator is going to look like that. And the really nice thing about convolutional networks is it allows you to learn a stencil. So that stencil is compact, which means that the convolutional networks allow weight sharing. And what weight sharing means is that you only learn parameters for this low dimensional stencil, even if you have billions of pixels within your image. So compared to a dense network, there's the attractive part is that you can is that you don't need as many parameters to describe a single layer. The issues with convolutional networks are that they require translation invariance. For example, you have to be able to slide this stencil over your data, which requires that you work with a pixel, a Cartesian grid. There's a question about how do you handle boundaries, right, where you don't have data for your 3x3 stencil in this example. And then there's a question about how can you actually embed physics information into this kernel, which we'll talk about some more later. So once you have a convolutional network, people stack these together into architectures. Typically, you know, in this classical MNIST example, you'll take your input image, you'll feed that into a convolutional layer, you'll apply max pooling and batch normalization layers, feed that into a dense network, and repeat that over and over again. So there's a lot of effort to generalize the successes of convolutional networks to unstructured data. And one of the main techniques is using graph neural networks. And so there's a lot of graph neural network variations out there. And I don't want to belabor the point too much, trying to distinguish between them. But the main point is that graphs are strictly topological objects to work with. So it's very difficult to incorporate metric information. And what that means is it's difficult to interpret convolutional layers as finite difference stencils. And the nice thing about finite difference stencils, they provide a connection to differential operators, and that provides a path to physics. So that's the main motivation that we have for developing a new tool here. And the tool that we're using is called Generalized Moving Least Squares. And the way GMLS works is that given a function u in a Banach space, it's an abstract framework for estimating operators tau. And the idea is that you're going to find an optimal reconstruction over some subspace P, some subspace of V, which best matches a set of unstructured samples. And here we write these unstructured samples in terms of sampling functionals lambda. And so this is a little bit abstract, but I'll break it down with an example. So the idea is first you solve a reconstruction problem, an optimization problem, which is a little L2 optimization weighted by a compactly supported positive kernel W. And then once you have that reconstruction, you hit it with the functional you want to estimate, and then that gives you a good estimate. Okay, so to make it concrete, the way it would work is, say for example, you want to approximate as a target the derivative of a function at a point xi. You could find a reconstruction over the space of nth order polynomials. You could build that reconstruction by sampling from a scattered point cloud of point samples. And as a weighting function, we can pick, you can really pick lots of different things, but here we'll just, and for the remainder of the work, we'll consider positive, this red bubble function. with compact support epsilon. So what that gives you is a tool for building stencils on scattered data. So for your reconstruction space, if you pick a basis, bold phi here, so that P can be written as a combination of this coefficient vector A and that basis vector. You can rewrite the reconstruction problem as finding the optimal coefficient vector that best fits your basis locally to your data. And then when you apply the second step where you look at the operator applied to your reconstruction, you can, when it's written in this form, you can see that it amounts to pairing two types of information. The first part is this coefficient vector A, and that coefficient vector provides a local encoding of data into your basis, into your reconstruction space, and then you're pairing that together with knowledge of how the operator acts on your basis. So you turn this crank, you solve this small local linear system, and what it will spit out for you is a set of stencil coefficients to approximate whatever it is that you're trying to approximate. So the trick to this is that you need to know how the operator acts on a basis. So for example, if you're looking at Taylor monomials, you want to approximate a derivative, it's easy to know the derivatives of Taylor monomials, for example. In this data-driven context, we're going to assume that we don't actually know how tau acts on phi, and we're going to try and parameterize that. But first, what we're going to do is just take a look at the, the forward simulation context, where we've done a lot of work with this over the past few years in traditional modeling and simulation. So to give a feel for how all that works, I'll just give a brief summary of that. So first off, this whole framework is supported by a rigorous approximation theory. So there's a lot of approximation theorists who've looked at special cases of GMLS, so particular choices of target functions, particular choice of sampling functionals, and so on. And so you can look at these results throughout the literature. Holger Wendland's textbook is an excellent textbook for giving an overview of everything. And you get certain convergence guarantees. For example, if you want to perform regression, you get that, and you're working with mth order polynomials, you get convergence order h to the m plus 1. So similar to what you would expect from finite element type things. So we've done a lot of work at Sandia, particularly Mauro Perego and Pablo Bocha. We've been working together on a project here where we're generalizing this for any choice of any general linear bounded target functional, any linear bounded sampling functional, kind of a abstract framework like a crank you can turn, and it will spit out similar approximation theory, truncation error estimates. And so what we're going to look at now is some examples of what we've done in a forward modeling context. So the first thing you can do is use this to generate finite difference type schemes. But the interesting thing about this, beyond being able to work with scattered data, is that you can tune your reconstruction space in order to engineer physics and mathematical structure into the problem. So in this example, we're solving the Stokes equations, and we're working with the velocity field, right? We need to approximate Laplacian of u and divergence of u. But what we're going to do is we're going to work with the space of divergence-free vector polynomials, which is difficult to do in traditional mesh-based context, but in the GMLS framework, it works really well. We've also developed conservative schemes. So it's a little bit subtle, but if you're just working with particle methods, you're only working with zero forms, and in order to make sense of conservation, you need a divergence theorem, which needs relationships between 2 forms and 3 forms in 3D, the Gauss divergence theorem. So basically what we've worked out is a way to embed point clouds, to endow them with abstract notions of measure, which represent a discrete Gauss divergence theorem. And this metric information is virtual in the sense that there are no actual volumes here. They're just numbers that are kind of cooked up in such a way that they guarantee conservation of fluxes and so on. Another area where we've used this is to solve surface PDE. And the really nice thing about GMLS is it gives you all of the information you need in order to work intrinsically on a manifold. So say you want to approximate something like a Laplace-Beltrami operator on a manifold. You can pick a point cloud sampling the manifold. You can pick one point, You can estimate a tangent plane using something like PCA. And then you can use GMLS to estimate the mapping from the tangent space to the manifold. And so once you have an estimate of that mapping, that provides you with everything you need, like a metric tensor, curvature, you can approximate surface gradients and so on. And so we've done some work using this to solve the Stokes equations on manifolds. Okay, so that was the forward simulation context. Now what we're going to look at is the data-driven version, where now we don't know what the operator is that we're trying to approximate. We're trying to learn it from some data. So what we're going to do is we're going to take this GMLS estimator, right, and recall that it is a pairing of GMLS coefficients, which encode your data in terms of a reconstruction space with the action of an operator on the reconstruction space. So what we're going to do now is we're going to parameterize this tau of phi function. So the way that that works is we're going to take our data, we're going to solve this GMLS problem in order to extract the coefficients. And an important point here is that this can be done as a pre-processing step. So you can sweep through all of your data before you go into TensorFlow or PyTorch or whatever, and you can do all of this highly parallelizable linear algebra in order to embed your data in terms of these coefficients. And so once we've developed this encoder, if you'd like, then we're going to feed the GMLS coefficients, right? So you start from your scattered data, that's your input channels. You feed that into your GMLS coefficients, and then you feed those GMLS coefficients into a dense layer, into a multilayer perceptron. And so that's equivalent to estimating in this GMLS framework, as it's equivalent to assuming that tau of h is equal to a multilayer perceptron acting on a coefficient basis. And if you choose for your dense layer a single linear activation layer, this reduces back the classical GMLS estimator, which has all this extremely nice theory. It also allows you to take deep layers, and then you can use this to parameterize nonlinear mapping. So once you have that layer, you can pop it right into into TensorFlow or PyTorch. We have code available online. The links are below here. And basically, you can just pop those layers in the exact same way that you would use convolutional networks. You can do max pooling, you can, and so forth. So, so to start off, we want to use this to do scientific machine learning, but to back up the claim that this actually does generalize convolutional networks, you can set up you can take data from MNIST and you can apply GMLS to that. So what we did is we took a standard architecture for convolutional neural networks, and we just swapped our GMLS thing in without improving the parameters or anything like that. And we got pretty comparable accuracy to what you could get with a convolutional network. And if you look at the output of each of the GMLS channels, you can see that it's identifying features in the same way that a convolutional layer normally would. So for what we really want, though, is to be able to handle engineering data. And so we're going to look at RAND simulations of turbulent flow past a cylinder. And so what we did is we took a finite volume code, we took OpenFOAM, we ran 200 simulations, and then we extracted the velocity field at the cell centers. And we trained on data that looked like velocity fields and the corresponding drag force on the cylinder. So in order to actually calculate the drag, you need the pressure, you need the viscosity in order to calculate it from first principles. But what people know from dimensional analysis is that you can actually collapse the drag coefficient for this problem onto a single curve, and that it correlates directly with the length of the recirculation zone. So the length of those eddies in the wake behind the cylinder that length scales with the Reynolds number, and that's sufficient to collapse your data down. So it's kind of remarkable that basically we have hidden physics that we're able to exactly capture this without telling it what the pressure field is, for example. So in terms of operator regression, this is another test that's a bit of a just a validation, but just to make it clear that you can regress operators. So basically what we did is we randomly generated, we drew Fourier series with random coefficients. We applied the operator to it. The operator's on the right, so we looked at a 1D Laplacian, a Burgers, as a prototypical nonlinear operator, and a 2D Laplacian as well. And it works as expected. There's a lot more details in the paper if you're interested in how exactly we set this up. So then what we'd really like to be able to do is use this to do operator regression for data-driven models. So the idea here is that we're going to do a simulation of Brownian motion at a particle level. So we take a periodic box, we run a short burst of MD simulation to evolve to a short time. And then we assume that, we make an ansatz that we're trying to find an operator which will update the mean particle density of this form. And we assume that this unknown operator L, we're gonna plug in a GMLS-Net there in order to approximate it. And basically what you can do is you run maybe 5 time steps of expensive molecular dynamics. That's enough to extract, for this problem, the homogenized solution is actually the heat equation, and GMLS is able to pick that up. I will point out that it's very important for this, though, to smooth the data. So basically what we're doing is we're taking particles, we're building a histogram of particle density, and just due to statistical sampling, there's a lot of noise in that data. So in order to make this work, it was necessary to apply a filter to smooth that out. Another interesting area is we might want to use this to do data-driven discretizations. So the idea here is, again, we're going to make an ansatz that we want to learn the advection diffusion equation, and we're coming up with 2 different schemes, one corresponding to a finite difference scheme, and another one corresponding to a finite volume scheme. And this is where it's really important that in GMLS you can work with, you can target phase fluxes, you can work with sampling and target functionals other than just point evaluations. You can work with higher order differential forms. So for both of these, what we do is we look at the exact solution to the advection diffusion equation. We evaluate that for a single time step, and then we use that as our training data. And what we pull out is, so that defines 2 different methods, and then you can integrate those methods for a long time. And what you can see is that if you were to just take, a standard finite difference method or finite volume method and discretize the advection diffusion equation, and because these are implicit Euler schemes, it's well known that that's going to be overly dissipative. And so you can see this dashed black line is what would come from a straightforward discretization of the governing equations. So the operators that we actually pull out, though, aren't dissipative at all. So you're able to take a CFL number of 10 without actually, and have an order of magnitude increase in the accuracy compared to if you just took a standard discretization and worked with that. So we've introduced GMLS-Nets. It's a new architecture that generalizes convolutional networks. It's very similar to, in spirit, to what a lot of people have been working on with graph neural networks, but it has some key advantages. So, it fixes the boundary issues and the problems with handling scattered data that convolutional networks have. You can work with the types of degrees of freedom that naturally come out of PDE discretizations, like traces for edge elements or flexes for face elements and so on. And it's embarrassingly parallel. So basically, it preserves the local structure, the local stencil that you have with from a convolutional network. Whereas, some graph neural networks you might have to solve, they're different flavors, but some you have to solve a global eigenvector problem for a lot of them. So the real benefit to this is that these are just sort of some first steps, but the main contribution that we think this has the potential to do is engineer physics more directly into convolutional net style architectures. So you can work within the GMLS problem. You can engineer properties you want into the reconstruction space. We're working toward taking our conservative forward simulations and our manifold or surface PDE simulations and see if we can actually do operator regression on in these spaces. So yeah, I'll leave it at that and take questions if there are any.
Okay, thanks. Yeah, awesome. Thank you. So if there are questions, so again, you can use the chat. You can relay a question or just then give you the floor. Or I have myself just a quick, maybe I'll just start with a quick question. So yeah, there was a nice trick here you had early in your slides about these coefficients A. I mean, it's a small thing, but so basically A is, what is that? It's a, these are polynomial coefficients basically, or in some basis, or what is it? Then, well, it's more the input for the neural network.
Yeah, right.
I mean, you don't actually, right, you have this, right, exactly, you have this A0, AN. So what is that exactly?
So each one of these, so it's a little bit abstract, right? So to make it concrete, let's assume that we're working with a polynomial reconstruction and say you're in 1D, and you're working with quadratics. So the basis would look like 1x squared, for example. The coefficients represent the best fit of your data to a polynomial in that space. So it really is like an encoding of, it lets you learn a mapping, instead of trying to work with a stencil directly, it lets you parameterize and work in the space of polynomials, for example.
Yeah, but this is I think this is a nice trick, because working directly with the points, values, and locations, I think would be kind of trickier.
Exactly. Yep.
Yeah. So can you go to the MNIST, sort of related to that, your MNIST example? I mean, it's not like super relevant, but so the A0, A14, what are those then that you're plotting here?
So this is the output of the GMLS layer coming from 15 different channels.
But A0, for example, it means you make A0, 1, because A0, A14, that's the input vector, right? Oh, it's the image. No, what is it? It's, I don't see what. What's
yeah, sorry, I pulled this from
no, your input is also an image with 15 coefficients.
Mm-hmm.
So it's sort of a tensor where each surface is an image, and then the depth is 15 for each polynomial.
So I think for this one, I believe we worked with quadratic polynomials for this one. The details are in the paper. So in that case, right, it's a dimension, it's 2D, right? So it's dimension 6 is the dimension of the polynomial space. And then this A, this was poor notation on my part. That's not, that A isn't the basis. That is just the output of the layer.
Right, okay.
Channels. Yeah.
Right, okay, so it's a usual, okay, representation of each layer after the convolution.
Yeah, it's the exact same thing as this plot in the bottom right.
Right, okay.
Convolutional network.
But the input are these quadratic polynomials.
That's right.
Okay, nice. So any other questions from the audience?
Hi, Nat. This is Lulu.
Yeah. Okay. Great. Yeah. Can you introduce yourself briefly?
Yeah, this is Lulu. Currently, I'm a PhD student from Brown University. Yeah, I have one question. So, one simple question. I'm not quite sure for all these applications, what's the input and output? For example, for this image classification, then the input is the image or others. And for the PD case, what's the input and output? Exactly.
Yeah, there's a lot of details that I glossed over that are in the paper. For MNIST, I mean, this is a standard MNIST. In this case, you have a pixel with an intensity corresponding to how light or dark each pixel is. For this one, you have the velocity field. It's a point at each cell center, and and a point evaluation of the velocity there. For this one, the output is just a scalar, right? So you're trying to learn a mapping from images of velocity fields to a single real number, right? Which is the drag coefficient. Is that clear? Is that?
Yes. Thank you. So another simple question. For this GMLS, the first field, the GMLS-Net, that part. So this only coefficients actually is not trained. It can be directly be fitted, so or computed. So it can be treated as a pre-processing, right?
Oh yeah, definitely, and that's exactly how. Maybe I should have stressed that. So in the TensorFlow code, right? So when you solve these least squares problem, right? And these basically just amount to inverting a small dense matrix. You can do this once for all of your data and then save it, and then for every step of gradient descent, for example, if that's what you're using, it doesn't have to resolve this over and over and over again. And so in the TensorFlow and PyTorch implementations that we have online down here, you can see that that's exactly how we have it set up. And I should also mention too that Sandia has a Trilinos library called Compadre for accelerating the solution of these GMLS problems on GPUs, and it works in Python. So you could, we're working on actually trying to accelerate this a lot. But as is just a vanilla serial implementation is pretty fast.
Okay, I just forgot, in this image, what's SD again?
SD is scattered data. So it maps from scattered data, it comes in through a GMLS layer that gives you the output of that lives on the point cloud, right? So that maps back to scattered data. And then you can stack these in the usual way.
And the MP, what's that?
Max pooling.
Is it?
Yeah, MP is max pooling, MLP is multi-layer perceptron.
Right. Okay, so any other questions?
Maybe another question. So do you compare this framework with graph convolutional network directly? So if we use GCN directly for this problem?
Yeah, that's on the list of things that we would like to do. For some of the thing is with a graph convolutional network, it's not like, basically we want to be able to start saying like, as a prior, we know that mass is conserved. So we're going to do a reconstruction over divergence-free vector fields, for example. You can't do that with a graph neural network. So we haven't prioritized making that comparison just because of where our interests are. But that is something that I definitely like to find out if it's competitive, or, you know, if there's pluses or minuses.
Thank you.